Okay, this is part 2 of our lesson, and we just finished talking about algebraic functions. And now we're going to look at what we call transcendental functions, and that's probably a new term for you as well. Transcendental functions are non-algebraic. So we just looked at how algebraic functions are produced by taking sums, products, and quotients of roots of polynomials and rational functions. So if we have something else, then it's transcendental. Examples of transcendental functions that you have seen are exponential functions, logarithmic functions, and trigonometric functions. But you might also have some other combination of something that is not considered algebraic, maybe like x squared plus sine of x as an example. It has something trig in it and it has something polynomial in it. That would also be considered transcendental. So let's go ahead and review exponential functions. What should we know about exponential functions? Well, as usual, domain and range, and the general shape, and the asymptotes, and the intercepts. Okay, so we have f of x equals 2 to the x. That would be exponential growth. Anytime you have a base that's greater than 1, it's exponential growth. I'm sure you can think of a scenario in which we've all experienced an exponential growth model situation in our lives in the last year. Think about the pandemic, unfortunately. So exponential growth looks like this. And for f of x equals 2 to the x, the y-intercept would be at 1. So it would go through the point 0, 1. Because 2 to the 0 power is 1. And the x-axis would be the asymptote. It just gets closer and closer to that line. So it has an asymptote. The x-axis has the equation y equals 0. The domain is all real numbers. You can raise 2 to any power. But the range is y is greater than 0. In this case, it doesn't touch or go below that asymptote. And then the other example, f of x equals 1/2 to the x, is not exponential growth, but exponential decay. So that would look like the reflection of the other one. It's going down instead of going up, but it would still have the y-intercept at 0, 1, because 1/2 to the 0 is 1. And it would still have the asymptote y equals 0. The domain, all real numbers, and the range y is greater than 0. Now, of course, if you transform one of these graphs, if you stretch it or shrink it or reflect it or shift it up or down, left or right, that could affect the domain and the range, and it could affect the asymptote and everything else. How about logarithmic functions? Well, it's really important to remember that logarithmic functions are inverses of exponential functions. So if you remember things about exponential functions, you can develop the ideas about logarithmic functions. You don't just have to memorize things about logarithmic functions. You can just figure it out, like domain and range and asymptote and general shape. Okay, so if you were to picture the graph of y equals 2 to the x, as we saw earlier, it looked like this. If we take that and we reflect it across the line y equals x, here's y equals x, we get our logarithmic graph, the reflection of the exponential graph. I made my line kind of sloppy, so it's not a perfect reflection, but you get the idea. So this is log base 2 of x. So what we see is there are no x values beyond the y-axis, so the domain is x is greater than 0, the range is all real numbers. And the asymptote, now since this is the inverse of the exponential graph, and the exponential graph had a horizontal asymptote, this has a vertical asymptote. Okay, so if you ignore my gray dotted curve, and you ignore my yellow line, and you just concentrate on the green curve and its asymptote there, this is the logarithmic growth function. the asymptote is x equals 0. And for logarithmic decay, very similar. We take exponential decay, which looks like this. We reflect it across the line y equals x, and we end up with something that looks like this, more or less. That's logarithmic decay. Get rid of the stuff we don't need there. So it also has a vertical asymptote, and it also has a domain of x is greater than 0 and a range of a range of all real numbers. And then, just like the others, if you shifted, stretched, reflected, and so on, you would change the domain, range, and asymptote potentially. Okay, trigonometric functions. We're going to actually spend a whole day reviewing trigonometry, so we're not going to do this today. So we are ready for our assignment. It's kind of a short assignment. I hope that doesn't bother you too much, but on the other hand, we had kind of long videos, so it all balances out. Thanks, everybody.